In this appendix video, we want to develop some of the ideas of differential calculus that we'll need in order to develop the theory of relativity. We start off with the idea of a function of one variable, f of s. This can be represented by a curve on a graph, such that if you give me any value of s, I can go up to the curve and figure out the corresponding value of f, hence f of s. As an example from physics, we might have position as a function of time, or velocity as a function of time. From this function, we can derive the derivative of f with respect to s. This is a measure of the slope of the graph. From our original point, we step to a nearby point where s increments by delta s. The line between these points forms the hypotenuse of a little triangle. The bottom side has length delta s, and the right side has height delta f, where delta f is just the difference in the function value at the 2 points. This triangle defines a slope, delta f over delta s, rise over run. And in the limit that those displacements become very, very small, they go to 0, we call that the derivative of the function. And we'll use a dot above the f to represent that derivative. We might also write this as df over ds, kind of a little change in the function over the change in the variable s. We can use this to figure out the change in the function when we make a little step ds. We have df is equal to f dot ds, that is the derivative or slope of the function times the little displacement ds. We also have the concept of the second derivative of a function f with respect to s, and this is a measure of curvature. In this case, we form 2 little triangles, one in the forward direction and one in the reverse direction. Each of these triangles has a corresponding slope. Then the difference of those slopes divided by delta s is a measure of the curvature of the function. If the function was a straight line, the slopes would be the same, and this difference would be 0. We write f double dot is the limit as delta s goes to 0 of the difference of those slopes over delta s. That's called the second derivative. That's a measure of curvature. So we have slope and curvature. We can also have a function of several variables. For example, a surface defined as a function f of 2 variables x1 and x2. And as we've discussed, we can represent this as a contour map. Suppose we take some point on the surface and ask, what is the slope at that point? Well, that's ambiguous, because it depends on which direction we head in. If we go to the right, we'll get one slope. If we go upward, we'll get another slope. And in general, every direction we go in will have a different slope. Now, if we decide to keep x2 fixed so that only x1 can change, then we're back to our function of a single variable, and we could use our derivative concept. Then the change in f, df, is the derivative, considering only changes in x1, times the change in x1, your dx1. And we could do the same thing in the other direction. Fix x1 so that only x2 changes. Now df is equal to the derivative that only takes into account the x2 changes times the change in x2, dx2. As a shorthand, we'll use the following comma notation. If we write f sub comma 1, that's a shorthand for the change or slope of f with respect to changes in variable x1. And f sub comma 2 is the change or slope in f with respect to variable x2. So now we can write, in general, the change in the function f, df, is equal to the change in the function when you only change x1 times the change in x1 plus the change in the function when you only change x2 times the change in x2. It's easy to overlook the commas, but it's important to note that those represent slopes with respect to the corresponding variable. We're going to call this the chain rule. And using Einstein's summation convention, where we automatically sum over any index that appears twice in one term, we can very conveniently write df is equal to f comma I dxi, meaning df is equal to f comma 1, the slope with respect to x1, times the change in x1, dx1, plus f comma 2, the slope with respect to x2, times the change in x2, dx2, plus so on, all the way up to however many variables we have. We can apply this to any expression. For example, if we want to know how our Christoffel symbol, gamma ijk, changes when we make a little change in position, we write d gamma ijk is equal to gamma ijk comma L dxl. We use L for our summation index because we've already used I, J, and K. Now granted, this looks very intimidating, but we'll see later on that we can very easily program a computer to do all the hard work, to keep track of the chain rule and the summation convention. All we need to do is just tell it what to do with these expressions. So here are the main mathematical expressions we'll need for the general theory of relativity. We have the metric idea, right? Our little yardstick invariant measurement ds squared is equal to gij dxi dxj, right? And you sum over I and j because they appear twice, the Einstein summation convention. We have the idea of the tangent tangent vector, which is like velocity in physics. Ui is just the slope of xi, just how xi changes with s. We have the Christoffel symbol, also called the connection coefficients, gamma I, j, k. We'll derive those later on. We see that these are related to derivatives or slopes of the metric tensor. The Christoffel symbols then show up in the equations of a geodesic, which will become the equations of motion in physics, which can either be written as the curvature of the ith coordinate is related to the slopes of the other coordinates through these connection coefficients, or the slope of the tangent vector or slope of the velocity is related to the other velocities. Finally, we have the Riemann curvature tensor, the most complex object we deal with. We derive that in a later video. Rijkl. It's derived from the Christoffel symbols, and you notice the common notation there. So it has to do with how the Christoffel symbols change with respect to displacements.